Okay, hello everyone. So today we have two speakers. So both of them from University of Southern Denmark. So the first one is Ali Meiler, and Ali is going to talk about correspondences, K-theory, and homology for étale groupoids. Okay, Ali, take the floor.
All right, thanks for giving me the opportunity to speak here. Been here for almost 4 weeks now, and it's been great. Going back on Saturday, so it's been a nice day. So yeah, I'm talking about stuff that's in my PhD thesis, but also some of it is on the archive as well. So and really the talk is going to be split into two halves. In the first half, I'm going to talk about what do I do with these things that I'm going to call, well, not I'm going to call, but people have called groupoid correspondences. And in the second part, I'm actually going to tell you what they are. I'm going to try to give you lots of examples to show kind of how general a framework they are for lots of different kinds of morphisms of groupoids. So what are they? And where can I find them? And my handwriting is not best, so if there's anything anyone can't read, just ask me, and maybe if I need to write bigger, etc. And feel free to ask questions at any point. Okay, so what I'm interested in is the following diagram. So we start with an étale groupoid. We construct the reduced or the left regular C-star algebra. And then we want to understand the K-theory groups of this C-star algebra. So this gives us a graded abelian group. So hopefully I don't need to convince many people here that it's worth studying the K-theory of C-star algebras. Maybe some of you still need to be convinced that it's worth studying groupoid C-star algebras. But really a lot of the time that we're studying C-star algebras and we want to understand K-theory, then there is going to be some groupoid sitting there to model the C-star algebra. Of course, we can construct them from things like Cartan subalgebras, which we have whenever we have a classifiable C-star algebra. But I think more generally, just lots of the situations also naturally come with a groupoid that you can use to describe things. And I want to try to understand the K-theory here with the use of the groupoid. So in terms of the groupoid, what can we say about this? And what I want to understand a bit better about this diagram is functoriality. So what kind of morphisms of groupoids can we take over here that are going to play nicely with this entire diagram? And it's not obvious, right? Because if you take groupoid homomorphisms, which are the sort of most natural class of morphisms you might look at for groupoids, which are just the structure preserving maps. So continuous and, you know, they preserve the unit spaces, and if things multiply together in one groupoid, then they multiply in the other one. This is groupoid homomorphisms. Then we're not going to be able to get star homomorphisms at the level of the C-star algebras. So if you think about groups, then this works just fine. A group homomorphism is going to give you a star homomorphism at the level of the C-star algebras. And it also works just fine for spaces, which are perfectly good groupoids, because a continuous map of spaces is going to give you a star homomorphism. The problem is they go in the opposite directions. So this is impossible to reconcile, and it just doesn't work. So we have to think of something else. So the groupoid homomorphism. So say we have groupoids G and H, and I'll get a bit more into how I view these later in the second bit of the talk. But we just want literally a function from G to H so that I guess what we want to say is that phi of GH or G1, G2 is going to be equal to phi of G1, phi of G2. And you need to ask for units to be sent to units in a way that this is going to make sense. But this is the kind of map I'm talking about. So really think like a group homomorphism, structure preserving map. So groupoids have structure and you want to preserve that structure. But the point is, if you just started with spaces here, well, this is the right notion of structure preserving map, I guess. So if we really want to look at these as sets with some operations on them, then yes, but we will see later that there are some better, this is one that doesn't work. So yes, I agree, there are some better ways to go about this. But certainly these, I'd say for most people, these are the things you'd think about first if you wanted to ask for morphisms of groupoids. In some contexts, they're the right things to look at.
Homology of groupoids, then or cohomology, it's fine. Groupoid morphisms, that.
So it sort of depends on if you're talking about homology of the homology that I'm going to be talking about.
Yeah.
Then no.
But like for classic ones coming in from algebraic topology, in algebraic topology, groupoid homomorphisms are like a fine.
Okay. Cool. But there is a notion of groupoid morphism that is used a lot in operator algebras. It's called a Morita equivalence or groupoid equivalence. So this is a kind of a looser notion of morphism for groupoids. It isn't some kind of just function between the groupoids. But this is great because thanks to Renault and Moley and Williams, we get a Morita equivalence of C-star algebras. So if we kind of follow this diagram here, Morita equivalence of groupoids gives us Morita equivalence of C-star algebras. And this is going to give us an isomorphism of abelian groups. And if you've ever tried to look at papers where people do things like compute K-theory roots of groupoid C-star algebras, you probably see this sort of thing happening where you take some kind of equivalence of groupoids and use this to say, well, the K-theory is the same. And the thing I'm going to be talking about is something called a groupoid correspondence. And from this, you can build something called a C-star correspondence. And these can often give you homomorphisms at the level of abelian groups. So I want to understand, I really want morphisms that are going to not be equivalences in any sense. I want something that is going to give us kind of one-way directionality for some categories here. So this is thanks to Holkar. And in the étale case, we've got Antunes, Ko, and Maya. And so if I just want to spell out what I mean here a bit more. Now. So suppose we have some correspondence. You don't need to know what it is yet, just that it's some kind of morphism. Then really you can build a correspondence of the C-star algebras. And here by correspondence of C-star algebras, what I mean is that you have a right Hilbert C-star of H module, and then some action on that by adjointables of C-star of G. And it's a fact that when these are proper, you get maps in K-theory. So I'm going to call this map here K star of omega. Right. So what I want to understand is, how can we understand this map K star of omega in terms of omega? So for example, when is this an isomorphism? So we know it's an isomorphism if, for example, this thing we start off with is an equivalence, because, yes, this is one thing I didn't mention, but groupoid correspondences generalize equivalences. So it's exactly the invertible correspondences which are equivalences. And obviously we're going to get an isomorphism when it's invertible over here by functoriality. So what I'm interested in is examples where we start off with something that's far from being an isomorphism, but we end up with something that is still an isomorphism at the level of K-theory. So it's going to enable us to do some computations. The other question is, what else can we do with these correspondences? So omega G to H. And George isn't here, but is theorem number 1. Which says that, so we know that we can get from a proper correspondence over here, we can get a map in K-theory. I've also got homology in the title. So what it says is that you can also do this for homology. So this homology is for ample groupoids. So we've got ample groupoids here. Now I'm going to add to this diagram here. I'm just going to add like ample groupoids. So these sit inside the class of étale groupoids. It's exactly saying that G0 is totally disconnected. So the space of, or G, if you like, is totally disconnected. Homology is a functor on these ample groupoids that is going to give us, again, some grade of the abelian groups, although they're slightly differently graded, because now we've got one of these for every natural number, or every integer, if you like. And we're sort of interested in how do these relate to each other. So people are interested in groupoid homology, at least in operator algebras, I think. They're interested in this because it has a strong connection to the K-theory, and there's a close analogy there. So this result is saying that the analogy holds strong for correspondences in that a proper correspondence, I should say étale here, from G to H is going to induce a map in homology. We're going to call that H star of omega. And this, for example, because this is functorial, this will recover the result that the homology of ample groupoids is invariant under Mauricio equivalences. Don't know. I think this is probably more accessible to most operator algebraists than going to the original paper where this is proved, and it's in a language that at least I find quite technical and difficult to understand. So I think this ends up being, in this case, a bit easier. All right, but why do I care about this map here? Well, it's really because my main result involves it. So I want to understand this map in K-theory. Map in K-theory we get over here. And what I can say is that it's enough to understand the one in homology, at least if it's an isomorphism. So I'm going to have two ample groupoids. And we're going to need two assumptions about these. So we need the isotropy groups to be torsion-free. So say you started off with a group, then you'd be just asking for the group to be torsion-free. And we need to assume that G and H satisfy something called the Baum-Kohn conjecture, which happens, for example, if they're amenable. So then if a proper correspondence induces an isomorphism in homology, then it also induces an isomorphism in K-theory. So if proper correspondence satisfies that H star of omega is an isomorphism, then we get an isomorphism in K-theory. Well, yeah, okay. So there's a slight subtlety here, which I brushed under the rug, which is that this thing is really only functorial for the full C-star algebras, unless you assume some kind of injectivity or some kind of, like with groups, for example, a group homomorphism is going to be functorial for the reduced C-star algebras, if and only if its kernel is amenable. So you've got a similar kind of thing going on over here. But yes, this is compatible with the map that you get at the level of the full C-star algebras. And when omega is sufficiently kind of amenably injective, I guess would be the way to say it, then yes, it is exactly that map that you get. Yeah, so you don't, because this is, so if you assume Baum-Kohn, then you can build functoriality for general group homomorphisms of the reduced C-star algebras, at least as the K-theories of the group reduced C-star algebras. So there's a bit of subtlety here. Yeah, so it's but yes, if you assume that you have this injectivity, then it would be exactly that. So why do we want this? Well, the idea is that the groupoid homology is in principle easier to understand. And what this means is that sometimes it actually is easier to understand. I mean, often people say, oh, in principle, this is easier to compute than this, and you have just two things which are horrendously difficult to compute, and you can't make any progress, which is, yeah, happens sometimes. But it might actually be easier to check that something is an isomorphism. And then you get the isomorphism in K-theory for free. So there are actually examples where you have some groupoids and you can see, maybe you can't compute the homology, but you can see that the homology is the same. And then as long as you can show that that actually comes from a proper correspondence, you get the isomorphism in K-theory. And I want to note that this has got some strong connections to things like the HK conjecture. But it's kind of, it fits into a broader context than that. So say G satisfies HK, if the K-theory is isomorphic to basically the direct sum of the homology groups of the same parity. And obviously now, if you understand the homology, then you understand the K. So clearly, if G and H satisfy HK, then an isomorphism homology gives you an isomorphism in K theory. But actually, you only really expect this to hold under more restrictive assumptions than go into this theorem here. So yeah, just got a bit of time to go over the brief history of this, which is you have counterexamples due to torsion. So I've assumed here that we have torsion-free isotropy, but really this is kind of the right assumption to make so that these things are even the right things to compare. And so Eduardo Scaparo found these counterexamples to this condition in this situation. But it is kind of true in low dimensions in some sense, at least when you assume your groupoids are principal. So they have no isotropy, let alone torsion in the isotropy. So, so I'm just going to say true for many, yeah, low dimensional principal groupoids. So probably I'd point to either the work of Proietti and Yamashita, or the work of Bernecker, Del Era, Geber, and Willett for this. But even in the principal setting, it's going to be false as you go to higher dimensions. So counterexamples, so principal counterexamples. So these are better than these ones because these ones had torsion. But now this is even principal due to Robin. So how about I say, so we got Robin, who's given a 9-dimensional counterexample, whatever that means. And Rachel Chaser is given a 4-dimensional one. I think this is work in progress. Or pretty much done, but still being, I don't think it's on the archive yet. So, okay, cool. So one thing that I find helps kind of clear up what's going on here is a theorem by Valerio Proietti and Makoto Yamashita, which says that if you make the same assumptions on the groupoids that I do over there, so ample with torsion-free isotropy and satisfy Kohn conjecture, then there's going to be a spectral sequence. So the second page is given by the groupoid homology. And it's going to converge to the K theory. Okay. So we don't really need to know what a spectral sequence is. It's just some homological gadget, which is building the right-hand side out of the left-hand side in some complicated way. So one of the things I like to compare it to is a short exact sequence. So in a short exact sequence of abelian groups, say, then the middle thing is built out of the things on the outer sides. So this is going to be times by 2. But you can lose information when you're doing this building, right? You can't determine this middle group just in terms of the outer groups. You really have to know more. So spectral sequences do a similar thing, but in a more complicated way, and it's much more, yeah, there's many more moving parts. But if you have a map of spectral sequences, and you know it's an isomorphism on this page over here, so in homology, then you actually get an isomorphism of the things that it's going to be converging to. And this is like with short exact sequences. If we have a map of spectral sequences, so short exact sequences, that we know is an isomorphism on each side, then it has to be an isomorphism in the middle as well, by, say, the 5 level. So this is actually what goes into the proof of my theorem here. So I just, what I do is I construct a map of these spectral sequences that they build. And then you can turn isomorphisms in homology to isomorphisms in K-theory. Yeah, so now's a good time for any questions, because we're going to move on to the second part of the talk, or actually define some things. Cool. So, a groupoid G, I'm not going to go into the definition, but I'm going to draw a picture. So really what I want to think about is that the groupoid is living on some space, it's space of units, G0. And I want to think of the arrows of the groupoid, so the elements of the groupoid as arrows, which I draw on this space, like this. So they have some source in the space, some range in the space, and then if I've got arrows that match up in the right way, I can compose them to get a new arrow like this. And I can do things like, say this element is Z, I've got an identity at Z, and I can do inverses. So this here with the G inverse. So a groupoid is where you can do things like this. And so, you know, if you only have identity arrows, you just have a space, G0. Or if you have only one identity, then you have a group. And these are the sort of the two extremes of a groupoid. Now, we have, yeah. So before it wasn't, the point before, and I explained this at the beginning, was that I'm talking about what I'm doing with things at first. And so the point is that they're groupoids, they're something that we're interested in, and we build C-star algebras out of them. So I guess I was talking about my results.
Okay, well, that's what I
Cool. And now I'm going to explain a little bit more about what these things actually are that I'm talking about. Cool. So an action. So just like with groups, groupoids can also act on spaces. And so usually we often learn a lot about groups by how they act on spaces. And the same true of groupoids, it's just a bit more fiddly. Sorry, I've just seen a comment there. Okay, sure. All right, so the way I want to think about a groupoid action is that we want an action map. So just like with group actions, we want to send an arrow and a space element for some element of the space. And we want to do this in a nice way. So if I draw the picture, then we have our space, an element in our space, and we've got our groupoid here with some arrow G in the groupoid. And I'd like to say, how can I decide what G dot X should be? So the idea is that in order for this to make sense, we have to have things match up, because it's not like with groups where just any arrow can act on just any point. We have to have some compatibility going on. And this is controlled by something called an anchor map. So this is a map from the space to the unit space of the groupoid, which describes how this is fibered over this space here. And the point is that we can act on our element X if X matches up with the base of the arrow. And then we can decide on some G dot X here, which is going to match up with the range. Okay, so actually, a groupoid action has two pieces of data. It's an anchor map. and an action map. And this takes a bit of getting used to. It's a bit weird. And for example, this means that if we just think of a space as a groupoid, then I've now defined for you what an action of a space is, and it's just a map into the space. So yeah, an action of a groupoid is going to kind of combine those two things, like the kind of the notion of a normal action of a group and a map into a space. And if you want to really get your hands dirty and understand why this is the definition, why this is the way it is, then I invite you to try to understand how the groupoid acts on itself by left multiplication. So, what should this anchor map be? Because we want to send a pair G and H to the composition GH, and then we should understand how should we do this. Because certainly this is an important G space. Okay.
The notion of a partially defined mapping the velocity. Is that what this is?
Yeah, so this action map is partially defined, and what's describing where it's defined is this anchor map.
Oh, sure, okay. There's a series of closed off and homology space.
Sure. Yeah, it's a pretty natural notion, but it does mean if you think of a space as a groupoid,
Right.
if you think of a space as a groupoid, then I've suddenly given you a definition of an action of a space, which is that a space Y acts on a space X by a map from X to Y, which is maybe not the most. If I asked you what should an action of a space on another space be, maybe that's not what you'd come up with.
You're presumably saying this fits into a picture. Fits into
It seems to be,
fits into a more general thing.
yeah, it seems to be the right way to let groupoids act on spaces when you're thinking about general groupoids. So, yeah, precisely. Yeah, exactly. Cool. So now I can define a correspondence. I don't. So an étale correspondence this is omega going from G to H of étale groupoids. So first of all, we've got a space omega, and we're going to have actions. So we have a left action of G. Okay, technically what I did here was a left action. You can imagine what a right action might be, and a right action of H. So these are going to have anchor maps. I'm going to write sigma for the source and rho for range. So first I need these actions to commute. So I need so this just means that G dot omega dot H is going to be equal to G dot omega dot H whenever enough of this makes sense. And we need the right action to be really nice. So this right action has to be free and proper, which freeness is, so these are like, there are these restricted definitions in the group setting, and it means very similar thing here. Properness, for example, is a niceness condition that ensures the orbit space is Hausdorff. And the last condition is étale. And what this means is that this is really a groupoid action definition because it's about the anchor map. It says that the anchor map is a local homomorphism. And this is really the étale bit. And I mentioned before, you know, if this is proper, then we get maps in K theory. So I need to tell you what proper is. And that's, so the left anchor map here, rho, has to be H invariant because the actions commute. So we get a map coming from the orbit space. Now this is just a map of spaces, so we ask for this to be proper. Okay. All right. So where should I go now? So H is a groupoid and it acts on omega, so you can think of orbits of this action. Just oh no, I hopefully didn't say Hilbert space. I don't know what I might have said in others. Yes. Okay. But we have a space omega, so this is a topological space. All right. Maybe this is the right one, so so now I need to give you some examples. So I've just given you a definition, which is not much use. So first class of examples I cover, as I said earlier, is Morito equivalences. So in this setting, we ask for both actions to be. So we have a correspondence, first of all, but now we ask for both actions to be free and proper. And we ask for more than just properness of this thing and properness of the sort of dual thing. We ask that this map here, which goes from one orbit space to the unit space, and dually this map here, these have to be homeomorphisms. This is one way to define groupoid equivalences. And there are loads of examples of these. I could spend ages giving you examples, but that's not the point of this talk because I want to talk about things which are not equivalences. But I will say you could have a groupoid acting on infinitely many copies of itself, acted upon by what I'll call the stabilization of the groupoid. And this is really the analog of stabilization at the level of C-star algebras for groupoids. So I'm just taking the product with what is the full equivalence relation on the naturals. So here I've just got my object space is the naturals, and I've got one arrow for every pair, for every ordered pair. Right. So then another nice example of morphisms or groupoids are open subgroupoids. So say I have G, an open subgroupoid of H, then I can set omega to be all of the arrows in H whose range is in G naught. So then we have an action like this, and an action like this, where these are really both acting by left and right multiplication, respectively. This restriction here is so that this action makes sense. And this is going to model our open subgroupoid, this inclusion, as a correspondence. So as this kind of very general kind of morphism.
There's no fun arrow, like for stable objects are written this way, but we're not really philosophical.
Mhm.
The
Yeah, if you have a subgroup, then so I would be talking about discrete groups because it's our groupoids. With a subgroup, yeah, in that case, the unit spaces are just both a point, and then this would just be this would be G acting on H, and just by left multiplication. So the third kind of morphism has many names. One name is algebraic morphism. Another name is actor. Another name is Zakajewski morphism. This is due to Bonacci and Statura, I think. And these morphisms are sort of I think these should be thought of as sort of the analogs of star homomorphisms. These are morphisms which are going to give you star homomorphisms on the level of C-star algebras. So what they are is you have your groupoid G and H, and now you just ask for this middle space omega to actually be H, and this action here just to be right multiplication. And this actually covers quite a lot of things. So for example, a group homomorphism, including a subgroup. So like that. But also a backwards map of spaces. So a backwards continuous map, let's say. So I've got X and I've got Y and I want it to go backwards. Because this is exactly what's going to give me an action of X on Y. But it also gives me maybe I'll leave this one up there as a reminder. This one, yeah. Another thing covered by these are a kind of groupoid homomorphism, but a backwards one. So this is a map from H to G that is continuous, proper, surjective, and fiber-wise bijective. And these were used by Xin Li to construct groupoid models of stably finite classifiable C-star algebras, every stably finite classifiable C-star algebra. These really give you conclusions on the level of C-star algebras, so an inclusion from C-star G to C-star H. So already this covers quite a lot, these algebraic morphisms or Zakajewski morphisms. And it turns out actually every groupoid correspondence is a combination of a Morita equivalence, an open subgroupoid, and one of these guys. So already this is everything, but there's going to be other things as well, which is sort of maybe you wouldn't realize would be some combination of these things. So actually we get homomorphisms in the forward direction. So following this étale means that as a map of spaces, I want this to be a local homomorphism. And then I'm going to be able to build a proper correspondence. Well, actually, one of these guys is going to give you a map in K-theory. I don't know how much people study that, but I think that's kind of interesting because often when you're working with étale groupoids, then lots of the maps you're working with are going to be local homomorphisms. So this seems sort of natural to me. But the last example I want to give is really the reason that I got interested in these things. And this seems to be kind of a genuine correspondence in the sense that I can't write it down as one of these previous examples. So I'm going to start with an inverse semigroup. It's going to have a space of idempotence E. And I can build a proper correspondence which goes from this groupoid here. And this is, so the inverse semigroup will act on its idempotence, whatever that means, and you can build a groupoid. And this is just a set. So this is going to be a discrete groupoid. Here, this just means non-zero. And it's going to map to, well, it also acts on the sort of the dual topological object to this algebraic object here. And we get a topological groupoid, an ample groupoid. This is often known as the universal groupoid of the inverse semigroup. So this is already cool. We really get a correspondence, and it's really far from being an isomorphism itself, because this thing is discrete. This thing has lots of topology. But the even cooler thing is that it induces an isomorphism in homology. So as a corollary, if you apply the main result, we have an isomorphism in homology. We get an isomorphism in K-theory if we assume some assumptions. So I'm going to say, under mild assumptions, under mild hypotheses, maybe, some people would disagree with me that these are mild. Particular, I need this thing to be Hausdorff. I didn't say, but everything here has to be second countable and Hausdorff, even though that's not true here. Anyway, under mild hypotheses, we get an isomorphism. So we can compute the left regular C-star algebra of the inverse semigroup through some formula. It's kind of like an orbit stabilizer thing. So we look at orbits of this thing up here. And now all we have to know is the left regular C-star algebras of some groups. So these are stabilizer groups for this action. And here, this group, you can really see it from the inverse semigroup. So it's all the things whose domain equals the range equals E. And sorry, I didn't say what inverse semigroups were. But if you want, they give you, if groups talk about symmetries, inverse semigroups talk about partial symmetries, but then you can still sometimes see symmetries within those partial symmetries. So this tells you that to understand the K-theory here, all you have to understand is that bit of it. And I just want to mention one last thing, which is that we can do a similar thing in the setting of left cancellative small categories, which some of you may have seen Chris Bruce talk about a week ago and the week before that. So for many of these, so again, it's going to be, mild assumptions. So left cancellative small categories, C, we can compute the K-theory of the left regular C-star algebra in terms of something discrete. So as the C-star algebra of the discrete groupoid of invertible elements. So this thing's really just a bunch of groups, and it splits up in a similar way to this. But yeah, that's everything I wanted to tell you about. So.